What impact is Kepler having on the field? Well, the first transiting planet was discovered in the year 2000. The first normal planet outside our solar system was only discovered in 1995. Just before Kepler launched, we learned about 70 other planets that were transiting their star. They're given here. And so on the bottom, you see orbital period in days. You see size relative to Earth on the left, on the vertical scale. You see images of Jupiter, Neptune, and Earth. And you see that almost all these planets are much larger than Jupiter, and they're all in very short period orbits. That's because that's the kind of planet you can find from the ground. Now, the smallest point down here at the left is actually detected by a space-borne photometer. It's a French mission called Keynote that was launched in 2007. In June of 2010, we released the first 4 months of data, and we announced over 300 candidates, which are shown here. And you see we're pushing down so planet sizes, approaching that of Earth, and pushing the orbital periods out to 100 days. That's because Kepler can stare at its stars almost all the time. You can't do that from the ground. In February of this year, we released another 3 months of data and brought the total candidate list up to over 1,200. And we're pushing that planet size down to well below Earth. Now, we haven't been able to confirm or validate all these, so I say planetary candidates, because you have to do follow-up observations to actually make sure it's a planet and not another astrophysical signal like an eclipse in binary. But we believe the vast majority of these are orbital planets, about 80 to 90% of them. Now, Kepler's laws tell you that if you know the orbital period and mass of the star, you know the distance from the planet to the star. If you know the size and the temperature of the star, which you can measure, then you can estimate the temperature of the planet. So we're very interested now. I've converted all these to equilibrium temperature versus size. We're very interested in this region here, which is the habitable zone. That range of temperature is where you can have liquid water. So in February, we had 54 candidates that were in this zone, and a few of them were quite small. And we're working to validate those. Now, since that time, in September, just last month, we announced the fact that we've identified, at this point in time, approximately 1,800 planetary candidates. So this is an explosion of extrasolar planets that's feeding a frenzy among astronomers to understand what this means in terms of planetary formation. You don't want to just find individual planets, we want to know what's going on. So I want to introduce you to Kepler 11, which is our most prolific planet host to date. It's one star with not one, not two, not three, but 6 transiting planets orbiting it. Now, this is a very flat system. And does anybody ever remember the old LPs about 11 inches wide? Anybody? Okay, so if you shrunk the system down to the size of an old LP, the planets would all stay within the vinyl. So for those of you who don't remember, if you shrink it down to compact disc, the same thing holds. It's a very flat system. Okay, it's compact too. The 5 outermost planets would all be within the orbit of Mercury in our system. The outermost planet is within the orbit of Venus. We're finding lots of multiple transiting planet systems. Over 400 of our candidates are orbiting only 170 stars. So we have lots of doubles, lots of triplets, lots of quadruples. Nature loves to make lots of small planets, it looks like. So we aren't quite down to Earth size and habitable zone because orbital period is about a year. We've only been up for 2.5 years. We need at least 3 transits, so we need to keep going. With big data come big challenges. So we have over 150,000 target stars. We collect 6 million pixels every half hour and store those. We download about 40 gigabytes of data each month. And at the end of the primary mission, we'll have 40 billion points in the time series. Now, that doesn't sound like a lot compared to some of the other astronomical surveys coming up. Fortunately, we're about 25 billion miles away, and we don't have a T1 line that runs that far. So it makes our job a little bit simpler. But there are big processing challenges for us. The instrumental effects are large compared to the signal of interest. The observation noise is not wide and it's not stationary. So the characteristics of the noise change over time. The way stars behave changes. And the search itself is very computationally intensive. It's an n-squared problem. We perform the scales with a squared number of data points you collected. So right now, with 2 years of data in hand, we performed about 8 billion tests to look for planets in one star like Earth. And at the end of 8 years, we have to 1,400 billion. So that's a challenge. Now, we do a lot more at the Science Operations Center than just run the science pipeline. I'll talk, so I just want to mention that. We have an infrastructure that's Java-driven that ingests all the data, controls all the flow of the jobs and then archives the data where it needs to go. And then we have the science pipeline, which I'll talk more about in just a moment. We also have to manage the targets. We only bring down about 6% of the data, so we have to know where each and every star is and where it's going to go, and make sure we get the right pixels back. And we have to track and trend and monitor the health and status and performance of the instrument itself. Okay, this is a panoramic picture of our pipeline. It's a set of multiple clusters. We have 64 hosts, 712 CPUs, about 4 terabytes of RAM, 148 terabytes of raw disk storage, and we're going to have to grow. It keeps on piling up. It's a scalable architecture for parallel processing of large data sets. It's pluggable, and each job is custom. We can make it parallel in different ways depending on what needs to happen. And we have to adhere to certain data accountability and parameter management by NASA dictates. And the job, as I told you about, the MATLAB integration makes it very easy for us to debug what's going on if we have a problem. We can actually run this on a cluster. We can also run it on a single workstation if we have a failed process, diagnose what's going on, and fix it very quickly. And we also are using the NASA Advanced Supercomputing Ladies facility at NASA Ames to actually do the search, because we've outstripped the ability for our clusters to do it in-house. So that's a remarkable capability that we have, and it's going to allow us to keep this up. So now I'd like to walk you through the science pipeline, how we actually get this data through and what it means. So we start out by calibrating the pixels. That's to remove on-chip artifacts and put on a linear scale with well-known 0 point to actually know how many photons you counted. Then we take the images of the stars, you see one on the left there, and we actually measure the brightness by summing up the pixels underneath the image. We also measure the location of the star very well, so that we use that for false positive illumination. And we take that data and we have to identify and remove systematic errors in it that are due to changes in thermal state and properties of the instrument. And that's very important. And at this stage, we're ready to do a search. I'll talk about that in a little while. And then when we identify transit-like features in the data, then we have to subject each of those signatures to a set of diagnostic tasks that either make or break confidence in the signature as a planetary nature. Oh, I forgot to mention, that was a picture of the pipeline. It looks just like a faucet. You turn it on, and the planet's just going right on. This is 1/2 of one CCD reactor, and I stretched it, flipped it to emphasize non-chip artifacts. So the vertical streaks you see are due to the fact we don't have a shutter. No one could design and build a mechanical shutter that we could guarantee would last for at least 8 years on the mission. So that's why we don't have one. That's one of the artifacts we have to remove. And then the illustration on the right there, you see the star image, all the black pixels, we don't bring those down, we throw them away. We only keep, it's like taking a yearbook from your high school or college, cutting out the pictures of your friends and putting them on a new page, and then throwing away the rest of the book. That's what we have to do because of the limited bandwidth we have to download the data. So we performed 7 different calibration steps at the pixel level. And you see some examples of the artifacts we have to identify and remove. Here where we have artifacts called undershoot, where it's quite strange electronic stuff going on. And we have crosstalk because we have a mosaic of many different chips being read out simultaneously. So we have to identify and remove that as well. So these are what some of the pixel connectors look like. Now, this star has a planet that was discovered the year before we launched. This is half P7b. You see the dips in the middle pixel time series there. This is brightness of the pixel as a function of time on the bottom. This is 10 days worth of data, and this planet is orbiting in a 2.2-day period orbit. So let's zoom in on these 3. So you see these dips that occur every 2.2 days are due to the planet crossing the face of the star. You can also see some other features. These are artifacts caused by pointing errors. We have to remove those as part of the processing.